Hello everyone. In this video, we are gonna go over the homework tree solutions with each other. I already uploaded the solution files in the on Canvas. You could find it on the home page under the module of homeworks. But in this video, I'm gonna explain a little bit more so we make sure that everyone is in the same page and we are okay for the midterm exam. Okay, let's start. In the question one, part A, the question gave us the phase voltage of a star connected, and phase voltage of an alternator, which is the VA is 231 with 60 degree, VBN is 231 with 180 degree, and VCN is 231 with minus 60 degree. And it asks us to determine the phase sequence of this three-phase alternator. If you remember before, the easiest way to determine the sequence is to draw the vectors that represent the three voltages, okay? The first one is the 231, okay, with a 60-degree phase shift. So the A voltage, the voltage of the phase A is gonna have 60-degree uh, uh, phase angle. The phase voltage of the phase B is gonna have the phase angle of 180, which is this line. So this is the phase B. And the phase C is going to have the minus 60 degree phase angle. So, and we said we are going to watch here about the order of the rotation of these three phases. And as you see, when you watch them rotate, you first see C, then B, then A. Okay. And we said this is rotational. Okay. So they are rotating. And you could see that C is basically following A, correct? Sorry, B, A, C. C is following A, okay? That means and B is following C. So CBA is equivalent to ACB, correct? So, and we know that the ACB is actually the negative sequence. So this is how we estimate the sequence of our system. Now, in the part B, it says in a balanced positive sequence, a star-connected alternator, we have our phase B. Okay, now it asks us to determine the phase A and C. So we know it's positive sequence, so it's gonna be A, B, C, meaning whatever voltage, whatever phase angle A has, the phase angle of B is going to be theta minus 120 degree, and C is going to be theta plus 120 degree. What happened? 120 degree, correct? So knowing this rule, and we have the voltage for B, so we could determine the theta, since it's balanced, the amplitude are the same, and since it's positive sequence, based on this rule, we could estimate the theta of the voltage of phase A and phase C based on this rule that we have for positive sequence. Let's move on to the question 2. In the question 2, the question gave us two circuits, okay? And we know that in a delta connected load, the Z of delta, each of the impedances are 10 ohm. And in a star connected load, the impedance of each phase is also 10 ohm. And in both circuits, we know that the voltage of the line, meaning voltage of these between each two lines, so this one, and this one, voltage between each two lines, which we call it line voltage, is 230 volts. Okay, now we wanted to like estimate or calculate the following parameters in each of those circuits. Let's start with the delta connection. It asks us for the line current, phase current and phase voltage in a load, and phase voltage and phase current at the source. Now, since it's delta connected, let's start with B because it's easier. Since it's star connected, we know that the voltage across each phase of the load, okay, is going to be equal to the line voltage because each load is actually connected between the two lines. So here, the phase voltage of the star connected, so in here, the phase voltage of the delta connected, sorry, is going to be the same as the line voltage, which is 230 volt. And since we know the voltage across each impedance, okay, and we know the amplitude of the impedance itself, we easily could calculate the phase current in delta connected by simply dividing the phase voltage over the impedances. So part B is very easy to calculate knowing the rules between the line voltage and phase voltage in a delta connection. Now, in a star connection, okay, uh, oh, sorry, let's go for the part A. Now that we have the phase connection, the phase current of each load in the delta connection, we already gone through that in the class that the line current is gonna have the same rule as the line and voltage in a star connection. So the line current in a delta connection is gonna be a square root of 3 times the phase voltage of the delta connection, the phase current of the delta connection. So we could easily, by this rule, we could calculate the magnitude of the line current here. Okay, and the theta, we know that it's gonna be plus 30 based on the rule that we discussed before in the class. So using this rule, we could also answer the part A for the first circuit. For part C, the phase voltage and phase current at the source, since the source and the load are in series, so the line currents in here is going to be in the load is going to be equal to the line current in the source. And we know for the star connection, line current is the same as phase current. Okay, so this phase current is going to be equal to this line current based on that process that we've gone through. For the phase voltage, we know the phase voltage in a star connection has that 1 over square root of 3 rule with the line voltage. So if we wanted to like calculate the phase voltage in a star connection, the amplitude is going to be 1 over square root of 3 times the line voltage, which we have, and the theta is going to be plus 30 that we talk about. So using these rules, we could we could answer all 3 parts for the first one. For the second circuit, let's try again. Okay, we are going to talk about the delta connection, the Y connection in the load and find out what is going to be the line current, phase voltage, and phase in the load, and phase voltage and phase current in the source. Now, we know the line voltage in the load is going to be the same as line voltage in the source because they are in series. Okay, and again, we know about the phase voltage and line voltage in a star connection, the relation that they have. So we could easily calculate the phase voltage in a star connection by using that 1 over the square root of 3 and plus 30 degree. Okay. And when we have our star connected phase voltage, because we have the impedance, we could easily calculate the current for the each phase of a star-connected load, okay? And so this is basically we answered the part B. And since it's a star-connected, we know the phase current and line current are the same. So by calculating that current, we already answered the part A, okay? Now for the source, we know that the line current, okay, between load and source are the same. And because the source is star connected, the line current and phase current are the same. So the same current that you find here is going to be the phase current for the part C. And for the voltage in the part C, for the source voltage, again, we use that square root of 3 proportion to reduce the low line voltage to the phase voltage in a star connection. Okay, so it's going to be, again, 1 over square root of 3 times line voltage, the voltage of each phase, and that 30-degree phase shift. So this is how we could answer the question 2. Now, for question 3, it says we have a balance. So far we know it's balance. Positive sequence, Y-connected voltage source. Okay, and we know the voltage AB, which means voltage between point A and point B, which basically is voltage of the line. Okay. For a balanced delta connected load, so our load is delta connected and each impedance is 30 with 30-degree ohm, okay, for each phase. Now, it wants the impedance of the line between the source and the load. So this line impedance is 3 with the degree of 3 ohm with the degree with phase angle of 60 degree. The question asks us to draw the per phase representation of the given three-phase circuit. We said, okay, since we know it's balanced, so we are over the step 1 of our analysis. Step 2 was to change all the, if we wanted to like have the per phase, we have to change all the deltas to star connection. Okay, so we have to have the equivalent star connection for this load. And we know that when we have the balanced system, the star impedance, the equivalent star impedance is going to be the delta impedance over 3. We've gone through that in the class. Okay, so each of these impedances are going to be 1/3 of the delta impedances. So our per phase system in the source, we don't have any problem because we already are in the star connection. Then we have our line, and here we have our equivalent Y connection, and we in both source and load we reach to the point neutral, so we could connect them, and we have our per phase system. Now, we calculated already the ZY. The ZL would not change, so it's going to be the same. But voltage of each phase, we don't have that. We only have the line voltage, but we also already know that in a star connection, the phase voltage is going to be 1 over the square root of 3 times the voltage of the line, okay, and that plus 30-degree phase shift. Okay, so this way we could determine the per phase circuit of this three-phase system. Very easy to answer if you follow a step by step. Now, in the question 4, the question told us that we have 3 similar coils. When it says similar, it means balance, okay? Each having the resistance of 20 ohm and an inductance of 0.1 Henry. And they are connected first in a star formation. So this is Y connection, star connection, and then in a delta connection. The frequency is 60 Hertz, okay? And they are all supplied with the 150 volt between the lines. So it's line voltage, okay? Now we want to calculate, okay, the total power absorbed and the line current in each Y and delta connection. Now, we have the frequency. First, you have to determine the impedances. We know the resistive part, okay, but for the inductive part, okay, for the reactance part, we have the inductance and we have the frequency, so we know it's j omega L, okay, so it's 2 pi f, and f is given, L is given, so you could calculate the reactance part, you have the resistive part, so overall you have your impedance as R plus J omega L. Okay, now that we have our impedances, let's try to calculate the values of the power and the line current. For power, we first need to have the current so we know how much current these loads consume. Okay, we know that the line voltages are 120, meaning the voltage between each two line is 120. Okay, in a star connection, we know that the voltage across each impedance is actually 1 over square root of 3 times in magnitude of the line voltage. Okay, so the voltage that each impedance experience across it is going to be in amplitude is going to be 150, okay, volt divided by square root of 3. And for the phase angle, let's uh, assume this one is the first one. This line is the uh, reference, so 0. So we know that the phase voltage is 30° behind the line voltage. So it's going to be minus 30° the voltage across this phase. Okay, now that we have the voltage across this phase and we find the value of the Z, we could calculate the current by the Ohm law. Okay, and since it's a star connection, we know that the line current is the same as the phase current. So whatever current that we have here is gonna be for the phase is gonna be the same for the line. Now that we have the line voltage or the line current and the line current, or in the phase one, the phase voltage and the phase current, we could calculate the power for this uh, three-phase balance system, which is 3 times of each voltage and the current conjugate. If you're using the line voltage, you have to use the line current. If you use the phase voltage, you have to use the phase current. And this way, easily you could calculate the amplitude of S. For the delta connection, again, we know that the line voltage is 150. And since they are the same impedance, so we already calculated the impedance in the previous connection, so we have the Z. Okay, but in delta connection, we know that each impedance in each phase of the load experience the line voltage across itself. Okay, so the current is going to be using Ohm law, this line voltage over that Z. This is going to be our phase current in delta connection. Okay, for each phase of the load. Now, for the line current, we know that the line current in a delta connection is a square root of 3 times that phase current. And delta-wise, it has plus 30° of phase shift. Okay, whatever phase shift this has, you have to have plus 30°, and then you have your line current in the delta connection. And now that we have the line current and we have the line voltage, again, we could use the formula S3VI conjugate to calculate the three-phase power since it's a balanced system, okay, and find out what is the power is. Okay, now you have the answers in the final answers in the solutions that I uploaded in Canvas. I want you to think about the numbers, the values of the power that you calculated, okay, in these two connection, and the values of the current that in each line these loads consume, okay? And try to think about when the difference between these values, okay, and try to think about what is the effect of having a delta connection versus a Y connection when we have the same load, so the impedances are the same, and we have the same source, the voltage of the sources are the same, okay? But by changing the connection from star to delta, how we could affect the magnitude of the current and magnitude of the power. Okay, I want you to think about that to see what is the significance of delta connection and Y connection. Now, in question 5, it told us that we have a balanced three-phase system shown here. Okay, and we wanted to make a Y connection or star connection for this balanced three-phase. We said, okay, we have 3 single-phase impedances or like solenoids that experience changing in a magnetic field. We talked about that from chapter 2, that each of these single phase A, B, and C solenoid would experience an induced voltage that wanted to like uh, oppose this change in the magnetic field. Okay, so using the right hand rule, we could determine what would be the polarity of the voltage that this change in the magnetic field would induce in each of these solenoid in each single phase. Okay, for example, in this one, if you use the right hand rule, we could find that the polarity of the voltages, for example, is plus minus, plus minus, plus minus. Okay, and now we want to have a Y connection. In the Y connection, let's uh, remind us about the Y connection. The Y connection is the connection between A, B, phase B and C, and the neutral point. Since the neutral point is going to be our point of like voltage 0, we normally consider the lower voltages connected to the neutral point. So it's going to be positive, positive, positive connected to the A, B, and C. Knowing that, and we wanted to like have a Y connection, meaning that all the terminals that have a minus polarity are connected to each other to represent the neutral point. So the terminal 2, terminal 4, and terminal 6 are connected to each other, and they are all representing the neutral point. And all the positive are connected to the phase voltages that we want to get out of this three-phase system. So point A, terminal B, and terminal C. So this way, we could connect in a Y connection. Same goes for the delta connection. If you wanted to like have the delta connection, you have to remember how these voltages are connected. So each positive is connected to the neighboring negative. Okay, so let's say we wanted to like have a delta connection here. Okay, in a delta connection, each positive is connected to the negative. So let's say we have here 1, 2, 3, 4, 5, and 6. So 1 is positive. The next one, the neighboring one, C negative is, the B negative, it doesn't matter. The C negative is the fourth one. So 1 is connected to the 4. Okay. And then C positive is connected to the B negative, which is 6. So C positive is 3, is connected to the 6. Okay. And then 2 is connected to the 5, the same values. And each of them would represent the phase voltages that we have. And in a delta connection, we don't have a neutral. So this is how we could like determine the connection in the terminals for each delta and Y connection. Okay, I'm gonna stop here. Please don't hesitate to email me uh, if you have any question. Again, I'm already uploaded the solution for this homework on a Canvas, so go over it. And the midterm exam is not gonna be anything more than all those homeworks. So if you are going over the homework 1, 2, and 3, and you understand the solutions, you shouldn't have any problem for the midterm exam. Thank you very much, and have a great rest of the day.